Hello, this is Satbir. The topic of our discussion in this video is calculating inverse matrix by Gauss-Jordan elimination. In the previous video, I give you the motivation of inverse matrix, and also I give you the definition when A is invertible. So A matrix is invertible if you can find another matrix, which is we call A inverse. When you multiply that matrix to the original matrix A, it produces the identity matrix. And this multiplication can be on the left hand side or either it's from the right hand side, it should produce the identity matrix. Not all the matrices have inverse. So A inverse only exists if the elimination produce n pivot. And also another property, if the matrix A, the inverse exists, it will be unique. Means A matrix cannot have more than one inverse. We have also essentially computed the inverse of the matrix. So the inverse of the matrix A was the multiplication of the diagonal matrix, which contains the diagonal entry as the reciprocal of the pivots. And then you multiply this diagonal matrix to the matrix 1, 2, elementary matrix 1, 2, 1, 3, and then 2, 3, and 3, 2, 3, 1, and E 2, 1. So these was the series of multiplication which produce the inverse matrix. In this video, we essentially use the name technique to compute the inverse, but we will organize our work a bit differently. So here I have an example where by 2 by 2 matrix, we will start calculating the inverse of this matrix. So my step number 1 of the Gauss-Jordan elimination is to first write this matrix as an augmented form. So what I will do, I will write this matrix 2, 3, and 2, 3, 10, 9, and I will write identity matrix on right hand side of it. So this is called the augmented form. So the Gauss-Jordan elimination, the idea of the Gauss-Jordan elimination is to eliminate first this entry, and then reduce all the diagonal entry into 1. So we will use the series of row operation to eliminate 10, then 3, and then make 2 and 9 into 1. So my first row operation will be on R2. It will be simply R2 minus multiplier, which is a 5 times R1. So if I operate this row operation on this augmented form, I will get 2, 3, 1, 0. This entry will go to 0. This will turn to -6. And this will turn to -5. And this will be R2 minus 5 times R1. This will be just 1. Okay. Now the next operation will be on R3, which will be on R1 to eliminate 3, which will be on R1 minus plus 1/2 times R2. So this operation will eliminate the entry 3. So let's apply this operation. So this will be 2, this will be 0. This will be R1 plus 1/2 times R2, means 1 plus minus 5/2. This gives you 3/2. And this gives you basically 1/2. Just you multiplying 1/2 and adding in 0. This is a 0, this is a -6. And this will be a 5, and that will be a 1. Now we will apply 2 more operations on R1, multiply by 1/2 times R1, and on R2, we will multiply by -1/6 on R2 to basically turn the diagonal entries into 1. So if we operate that operations, we will get 1, 0, 0, 1, and this will be minus 3 over 4, 1 over 4. This will be 5 over 6, and this will be 1 over 6 with a negative sign. So now, as you can see, that we start from the identity on the right, and now we produce the identity on the left. Now this matrix will be our inverse. So A inverse, which you can basically verify even multiplying that to the original matrix, minus 3 divided by 4, 1 divided by 4, 5 divided by 6, negative 1 divided by 6. This is our A inverse. You can also verify whether you got the correct inverse by multiplying A inverse to A. It should produce identity matrix. And also, if you multiply A inverse, it should produce the identity matrix. So this is how you calculate the inverse of a 2 by 2 matrix by using the Gauss-Jordan elimination method. Next, I have a theorem. So this theorem says that the inverse of the 2 by 2 matrix exists if AD minus BC is non-zero, and you can calculate the inverse of by using this formula. Okay, let's prove this theorem. We will prove this theorem by using the Gauss-Jordan elimination method. So very first step of this method is I will write this matrix as augmented form A, B, C, D. And I will write on the right hand side identity matrix. And I will operate on R1, R2 first to eliminate this C. So my operation will be R2 minus C divided by A times R1. Let's calculate the new augmented matrix after this operation. So the new augmented matrix will be A here, B here, 1 and 0 here, because no operation is applied on R1. R2, so this will become 0. So you are applying on R2 means the D minus B, C, A. And this will be minus C divided by A, and this will be 1. So you will turn this augmented matrix into this after applying this operation. So I will simplify the expression a little bit. So this is A, this is a B, this is a 0, this is a D minus BC divided by A. This is a minus C divided by A, and this is a 1. This is a 1, 0. This is our simplification of the expression. Now let's apply the operation on R1 to eliminate this entry, which is B. And to eliminate B, our operation will be on R1 minus the multiplier. In this case, the multiplier will be B divided by AD minus BC divided by A. So it will be basically BA divided by AD minus BC times R2. So let's apply this operation. So after applying this operation, so I will get A here, 0 here, 0 here, and here will be AD minus BC divided by A. And on this expression, this will be C minus A as it is. The 1 will be as it is here. And that operation will be 1 minus BA divided by AD minus BC, and R2 is minus C divided by A. I will simplify this first, and this will become basically A will cancel out, and this will become 1 minus minus plus BC divided by AD minus BC, which will be AD D divided by AD minus BC. After simplification, this expression will be AD minus AD minus BC. This will be BA with a negative sign, AD minus BC. And in the last operation, we will divide this entry by A. So this will be 1, 0, 0, 1. And if we divide by A, it will be AD divided by AD minus BC. And that will be minus B divided by AD minus BC. If we divide by AD minus BC on the last one, so this will give me minus C divided by AD minus BC. And that will be basically A divided by AD minus BC. So as you can see, this is our inverse matrix, A inverse. So if I write down this, so let me get my A inverse matrix. So now my A inverse matrix is D divided by AD minus BC and minus B divided by AD minus BC, and it's minus C divided by AD minus BC, and A divided by AD minus BC, which is equal to 1 over AD minus BC. I can pull out that term, and this will be D, here will be A, this will be minus C, that will be minus B. And this completes the proof of our theorem. Here is your first quiz problem. Please pause the video for 1 and 2 minutes and work on this problem. Next, we will calculate the inverse of 3 by 3 matrix using the Gauss-Jordan elimination. So the process is same, it's just we have the higher order matrix. So the solution, we will begin by writing down the augmented form. 2, -1, 0, -1, 2, -1, 0, -1, 2. And I will write the identity matrix 1, 0, 0 here, 0, 1, 0 here, 0, 0, 1. So this is the first step of our Gauss-Jordan elimination, is to write down the augmented form. Now I will operate the two-row operation. The first will be on R2 and then will be on R3. As you can see that since this entry is already 0, so I don't need to operate on R3, but I must need to operate on R2. So or R2, it will be R2 minus the multiplier. In this case, the multiplier is a -1/2, -1/2. So I will add 1/2 in R1. R3 will be same because there is no need any operation on R3 to eliminate 0. So after applying these operations, let's calculate our new augmented matrix. This will be 2, -1, 0, 1, 0, 0. This entry will become 0. This entry will become 3/2. This will become -1. This will become 1/2, 1 and 0. And there is no operation on R3, so it will be basically same. So after applying on R2 operations, this will be a new augmented matrix. Now next we will eliminate this entry, and this entry, and this entry. Now next we eliminate this entry, so we will apply the operation on R3, and the operation will be basically R3 minus the multiplier. In this case, the multiplier is entry to be eliminated is 1 and the pivot is 3/2. So multiplier will be 2 divided by 3, and in this case we will add in R2. So this will be a row operation which will eliminate -1. So after applying this row operation, your new augmented form will be 2 -1 0 1 0 0 0 3/2 -1 1/2 1 0. And once you apply these operations, you will get 0 here, 0 here, and this entry will be 4 divided by 3, and this entry will be 1/3, this will be 2/3, and this entry will be 1. So this will be your new augmented form after applying that operation. Now the next goal is to eliminate this entry and this entry. So we will be operating on R1 because R1 is already 0 entry, so no operation on R1 is same. But on R2, the operation will be basically, because in this case, the pivot is 4/3 and entry to be eliminated is -1. So -1 divided by 4/3, which is a -3/4. So I will take R2 and add 3/4 in R3. So this will be our operation to eliminate this entry. So let's apply this operation carefully. This is a 2 -1 0 1 0 0. This will be 0. This will be 3/2, and this entry will become 0. This entry will become 3 divided by 4. This one become 3/2, and this entry will become 3/4, and no operation on this. 1/3, and this is a 2/3, and this is a 1. Okay, one more operation to eliminate this entry, which is a -1. So next we eliminate this one, and our operation will be on R1, which will be basically, now the pivot is coming from here. So this is our pivot. So R1 minus plus again, entry to be eliminated is a -1, and this will be 2/3 times R2. And after applying these operations, our new augmented form will be 2 0 0, and on the top row it will be 3/2, and then 1, and then this will be 1/2 here, and this will be 0 3/2 0, and this will be 3/4 3/2 3/4, same, no operation on here, 1/3 2/3 and 1. So this will be the augmented matrix after applying these 3 row operation. The next we have to apply the last 3 row operation in order to basically make the diagonal entry 1. So these row operations simply will be on R1, 1/2 R1, on R2, 2/3 R2, and on R3, 3/4 R3. After apply this row operation, our augmented form will be 1 0 0 0 1 0 0 0 1, and the matrix on the right hand side will be 3, 4, 1 half, 1, 4, and this will be 1 half, 1, 1 half, and this will be 1, 4, 1 half, 3, 4. Now the matrix on this side is our inverse, so we can write down what is inverse. So our A inverse is, therefore our A inverse is 3, 4, 1 half, 1, 4, 1 half, 1, 1 half, 1, 4, 1 half, 3, 4. So rewrite this as a 3, 2, 1, 2, 4, 2, 1, 2, 3. So this entry, it will appear in the next next video. 1, 4 is important. As you can see that this entry is the multiplication of your pivot. So I'm gonna call this entry determinant of A. As you can see, that is the reciprocal of your multiplication of the pivots. So you have the pivots in the very last matrices, which we turn into the diagonal matrices, which is a 2, 3 half, and this is a 4 third. If you multiply all them together, this is equal to 4. So the product of the pivot are also known as the determinant of the matrix, which we will discuss in the next few videos. This is our quiz problem number 2. Please pause the video for 1 and 2 minutes and work on this problem. Here is a one property of the product of the inverse. If you have a two matrix A and B, both are invertible. In order to calculate the inverse of the product of A and B, you can use this formula. So product is calculated by multiplication of the inverse of the B matrix first, and then the matrix A. This is the end of the video. Thank you very much for watching. So I will see you in the next video.